What are you gonna do?
Good evening, everyone. Am I audible? I have muted everyone because for some people the microphone was on. So if you want to ask something, you can raise your hand. Then I'll unmute. Otherwise, you can message in the chat. I hope I'm audible. Yeah. Okay. I'll just wait 2 minutes to for more people to join. Yeah, we will be recording this session. And you can see in the NPTEL where I mean the Swayam portal, where you watch the video. At the end of all the videos, there will be a link to access the problem solving session. So there, when you click on the link, it will lead to an Excel file. And in that Excel file, you will have the YouTube link to these uh, recordings from Tuesday 7 p.m. to 9 p.m. And also there will be, you can access the slides that I'm going to use in today's live session. So both the things will be available on the Excel file in the Swire portal. Okay. So before we start, I just want to know, like, briefly, what everyone's background is. So can you put in the chat what your background is, whether you are doing bachelor's or master's or a PhD or something else? And what are you doing on? So if you are doing a bachelor's in engineering, what is your core? Like, is it, are you from computer science stream or electrical engineering or any other specific stream? Um, or if you are not at all an engineering student, what other uh, degree you are doing and also the subject that you are specializing? You can post it in the chat. Ram Mohan Reddy, you want to ask something? Okay, if you are raising hand, I would assume that you want to ask something. Okay, see that many of you are already from computer science or AML background. Okay. Uh, so I, yeah, okay. Yeah, so I am Parvati. I am also a student. I am doing my PhD in the Department of Applied Mechanics and Biomedical Engineering at IIT Madras. Uh, I work on using machine learning models for my study. I'm also working on some data analysis related project related to stroke patients. Yeah, so I hope uh, these sessions will be helpful for all of you who are trying to learn. And also, I just wanted to ask how many of you are attending the exam for this subject because they might have some deadline for the registration. Yeah, okay. Okay, around 10, 12 people, I think, from this session. Oh, sure. Yeah. This session, it will be a problem solving session where we try to discuss what was discussed in that week's lecture. So today it will be mostly on week one. Whatever we can discuss in week one content, we'll discuss it today. And then, yeah, okay. And then, if we get time, we'll discuss some of the questions that can be asked from that part of or this week's content. So every week there will be this live sessions from on Tuesdays from 7 p.m. to 9 p.m. So if you're not able to attend any of the sessions, it's fine because the recording will be already available in the YouTube, and the link to the YouTube video will be there in the Excel file in the Swayam portal. All the other exam related details and certificate related detail, exam registration, all these details, if you see in the Swayam portal, you can see before the week one video, there is a detailed set of videos that explain all these details. So if you have any doubt regarding the admin related things, you can check there about the exam, about the registration, all those things. Uh, so another question to ask is, did all of you watch the contents, the videos from week one? Okay, this is good. I think many of you have watched the videos, so it will be easier to discuss. Then maybe we can start with the contents. Um, People keep coming, so I have to admit. So the session usually start at 7 p.m. and I'll wait for 5 minutes and then we start the session. Okay. So have you all have you all I feel that most of you might have used this sklearn package for doing some machine learning related prediction, machine learning related prediction or some modeling. Um, so yeah, so uh, while you have come across such packages, have you ever thought of what is going behind this package? Or have you ever, like, how many of you have done some prerequisite courses before using some already existing packages like Xscaler or TensorFlow? So, most of us might have studied linear algebra, probability, some calculus in the first few years of our engineering degree. And then we might not have any connection with how it is used uh, with respect to machine learning. So this course is that connecting link there, which will tell you uh, how machine learning make use of the concepts in linear algebra, probability, optimization, statistics, etc. So packages So a package is something like a library. So if you know, for example, in Python, uh, if you have used Python, you will already use some pre-existing script that you can make use of to accomplish some task. So this is what is called as a package. For example, scikit-learn is a package that helps you use machine learning models without writing any code. I mean, you have to write some code, but that is just to import the already existing functions and libraries. So uh, this is a package that you don't have to write anything from scratch. There is already existing thing that you can make use of. So some of the machine learning packages are the scikit, TensorFlow, etc. Uh, no, it's not mandatory. I think you can check in the course requirements. I don't think it is mandatory to have an in-depth knowledge. So I'm sorry, I can't type. If I keep typing, then it will take a really long time. Um, so you can watch the video later if you want to, if something is not clear to you. Okay. So, yeah, so in this course, as the professor mentions in the video, you will be going through lectures on linear algebra followed by probability, and then statistics and calculus and optimization. So this first 4 weeks will have concepts on linear algebra, which will include vectors and matrices, followed by probability, which will allow us to quantify the uncertainty in prediction and classification. All this you will come across in the coming lectures. Then statistics and also optimization, a few lectures. So, everything in machine learning is revolving around this four tasks: classification, regression, dimensionality reduction, and density estimation. So classification, for example, is where you want to classify, for example, you have a set of images, you want to classify cat from dog. So that is a type of classification where you have some labels or a category and you want to distinguish one label from the other. So that is classification. Whereas regression is where you want to predict some actual value, a numerical value, such as, for example, predicting the stock price or predicting the price of an apple from some past history. So this will result in a numerical value prediction. So that is what regression is. Then dimensionality reduction is where you have a very large amount of data, but you want to make it, you want to make it in a condensed or a compressed representation so you can understand the data in a better way. That is dimensionality reduction. Then density estimation, you want to understand how the data is generated. So the models that handles such um, I mean, such tasks such as where the data is generated from deal with this density estimation concept. So all this is built on shared mathematical foundation, which includes this linear algebra, calculus, probability, analytical geometry, which includes calculating distance, angle, etc. So all this is the basic for machine learning. Now coming to data in machine learning, uh, you so what is a data means it's just a value that you get uh, from somewhere. For example, if you have a smart band, most of us use this smart band that will tell us how many steps we took today. So this makes use of a sensor that continuously record your steps, right? So each of this value that is recorded or measured every second, that is a data, that is a measurement. So that is data. And when you collect data with respect to a variety of factors, for example, your smart band can contain not just the number of steps, but it can also contain other factors. For example, it can measure your heart rate. It can measure your oxygen level. All these things are there. So all this corresponds to different variety of measurements, right? So if I combine all this different variety of measurement, I get an array of numbers, a list of numbers. And this list of numbers, we can call it as a vector. So if we take a patient's measurement and if we ask the patient to take a set of tests that include the blood pressure, the blood glucose, pulse rate, heart rate, all this, you get some values from the results. These are this 128, 96, 72, 74, 98, etc. So you keep all this together and you get an array like this 128, 96, 72. This list, this is the vector. So it has how many values? It has 5 values. So we say it is a vector with 5 components. So then this is just one patient. So we take data from multiple patients, say 100 patients. So from all the patients, we collect data from their BP, glucose, pulse, their heart rate, their O2 level, everything. And then we combine all this data and then we get what? When we combine all these vectors, we get a matrix. So this matrix is what we use mainly in machine learning. This is what we get in the form of this this is what we get in the form of this CSV file, the Excel file, etc. So when you do any machine learning task, you need some data. This is that data where uh, you will have a matrix which contain different features and different samples. For example, if we take the sensor readings from the smart band, each person can represent one row in that matrix, and each of the column represent one of the feature that the smart band is measuring. So this is so this you can this the smart band makes like it can be made accessible to you when you use the phone. I'm telling this example of smart band because I feel that most of us use it. So when you connect the smart band to your phone, you can access all this data in your phone. You can see all these graphs, you can see the prediction and all that. So this is what the data is. This matrix is what is corresponding to data. Yes, the components of the vector can be of different units. There is no issue with that. But then later, when you learn the actual pre-processing parts in machine learning, you come across something called as standardization or scaling, where if you have components of different units, and if the scaling is very drastically different, then you standardize it to the same range. At that time, there won't be any problem. So this is something that comes later. But for now, you can understand that yes, the components of the vector can be of different units. So one example that the professor talks in the video is about linear algebra in action. So suppose so the real world, yeah, so overall we need components in the similar range, but that comes later. This is at the very high level that you can have components of different units. But when it comes to so again, the question is overall, we need components in a similar range. It depends again on the model. So for example, if I use some machine learning model such as neural network or linear regression or logistic regression, etc. For those models, they are very sensitive to some of the optimization that happens in the model. So at that time, this standardization or making all the values in the vector in a similar range is something that matters a lot. But for some other models, for example, the tree-based model such as random forest or light gradient boosting machines, etc., they don't need the components to be in the same range because the optimization that they use is kind of different from the optimization that some other model use. So again, it depends on the model that you are using, that some components, some models need the data to be standardized, but some models, even if the data is not standardized or in a similar range, it is fine. They will work fine. So we have not reached that part, but this for now you can understand that the vectors can contain components of different units. Uh, so now coming to so the professor discussed about linear algebra in action like similarity. So if you have uh, two documents, for example, you want to verify that okay. One example could be you are given an assignment and you did the assignment. Another student also did the assignment, and some of the students have copied some other student's assignment. So you want to verify whether they have copied the assignment or not. So it's like a document verification. Um, so in this case, you can treat one document as A and another document as B. And if the contents of these two documents are same, then that means an example could be that the angle between these two vectors will be 0. So that means they contain the same content. That means the vectors A and the B, that is the document, contain the same things. Then the angle will be 0. I mean, in so we have already studied this concept of dot product where you have two vectors A and B. And if the angle is 90-degree, we have studied that they are orthogonal to each other. And if the angle is 0, then they are identical. And if the angle is -1 degree, then they are in the reverse direction. So all this we have studied. Now conceptually, what does it mean in terms of vectors or data is that whether it contains any redundancy or not. So that means, is it the same content or is it the same information that is there in the vector A and B? So is vector A contain the same information as vector B? That we can know from the dot product. So the dot product will kind of tell you, is there a similarity between two vectors. Now this we can make use of many this we can make use of in many concepts in machine learning, which we will study in the coming lectures, or we will study in machine learning. Uh, so then another thing is where probability is usually used. So you have made some medicine and you have experimented it on a group that actually received the medicine and did not receive the medicine. And you found that there is a 90 percentage success rate. So you can explicitly make some probability estimates using these concepts. So when you make a prediction model, there is a chance that you can tell from the model that there is a chance that the model is correct 90 percentage of the time, but the model is incorrect 10 percentage of the time. So these things is where the concept of probability is used. And then another statistical reasoning part where you tell that correlation is not the same as causation. So you tell that it is like the dog is barking, so it might rain today. So there might be in the past, there might be days where when the dog barked, there was rain, but it doesn't tell you that the barking of the dog is the reason for raining today. So there is a correlation between the dog barking and raining on that day, but it doesn't mean it is the thing that caused it to rain today. So correlation always does not lead to causation. So many of these machine learning models, if you see, they always, they come up with, so you have some input, you have some output. They find a correlation between the input and the output. They don't tell you that this is what caused the output. It's always a correlation mapping. It doesn't tell you uh, exactly that this is what it is caused. So for that thing, you have to go into causal models. So this is one thing that is the foundation, and another is optimization, where you use many algorithms that can help optimize different parameters of the model. So, for example, if we take the linear regression, you have to fit line a line that explain the relation between the input and the output. So, a line has an expression y is equal to mx plus b. So, this x is your input and the y is your output, and you have a set of data points. Uh, so, you want to find the line that separate the cross from the circle. This is that line. This is the expression of that line y is equal to mx plus b. But you don't know the parameters of this line, that is m. You don't know what is m and you don't know what is b. So, how do you find it? You have to find this line that optimally classify this set of points from this set of points. For that, you need to find this line with parameters m and d. So, you want to find the parameters that will classify this in a way with very less error or very high accuracy. So for that, you have to make use of some calculus. There are some algorithms like gradient descent and all that. So all this comes from optimizing something, some parameter, and this is where the calculus comes into play in machine learning. Yeah, so then in the video, the professor also talks about the split of different contents. First 3 weeks will be on vector spaces, then linear transformation, eigenvalues, eigenvector, orthogonality, projection, SVD, and then there will be a session on principal component analysis and support vector machine, followed by probability, three weeks content, and then 2 weeks content on calculus, followed by some basics on neural networks and classification, clustering, and regression. Okay. So since most of you have already watched the contents of week 1, uh, I'll start with asking what is a vector? Okay, it's a list of ordered numbers. It's like an array. Okay. Yeah. So it is something that represents magnitude and direction. It's an ordered tuple whose elements are taken from a defined field. Definitely you have watched the video. Yeah. So a vector, from school we have studied that it is a quantity with the magnitude and direction. It is something that we always draw with an arrow with some length depending on the coordinate system that we are currently dealing with. So if I consider a 2D system and I have x1 and x2, so then a vector I can tell is a two component array or a list of number where if I have, so by two component I mean one component along the x direction and one component along the y direction. So if the value of that component is 2 comma 3, that means 2 units from the along the x1 and 3 units along the x3. So usually the starting point is origin. So it just means a couple of numbers. Okay. So that is a two component vector. Now when it comes to an n component vector, it will lead to uh, an n number of components. So from the example that we have already seen, a patient's measurement, it is a 5 component vector, and when we combined all the data from all the 100 patients, it became a matrix, and the size of that matrix is 100 by 5 data matrix. So now the question is, how do we actually construct a vector? So then here is where we deal with the, I don't know, maybe for some of you, this might be a new concept on what is a field. So a field is a non-empty collection of elements with two operations. One is field addition. Another is field multiplication. So there are six property as discussed in the video. There are six properties that defines what a field is. And this sixth property, the first one is there exists a zero element such that for any element in the field, that element plus zero will always yield the element. So if there is an element called A from the field, that element plus zero will always result in A. The second property is that for any, so that is the additive identity. The second property is that closure under addition, that is for any A and B. So if I take two scalars A and B, then A plus B is also in the field. For example, if I take the set of real numbers, I take 2 and 3. I add 2 and 3. So 2 plus 3 is 5. 5 is also a real number. So there is closure under addition. That means for any number you take from the field, A plus B will be also a number in that field. So that is closure under addition. Then additive inverse. For every A, there exists a minus A such that A plus minus A is equal to 0. That is, you take any element A, you add it to the additive inverse of it, you get 0. Then multiplicative identity, you multiply any element with 1, you get that element. That is A times 1 is A. That is multiplicative identity. Then closure under multiplication, that is for any A comma B, A into B is also in the field. It is closure under multiplication, just like we had addition, closure under addition, closure under multiplication. Then multiplicative inverse, just like additive inverse, for every non-zero, there exists an inverse such that when you multiply a number by the inverse, you get 1. So this is when a set satisfy all this all this property, then we can tell that it's a field. So then in the lecture video, there are some examples on uh, field. First one is real number a field. So there is 0 in real number. So that is the field. That property is satisfied. Sum of two real numbers is a real number. So that closure property under addition, that is satisfied. And every real number has a real additive inverse. If I take 1 and if I take the inverse of it, that gives it 0. It is -1, and -1 is also a real number. Then product of two real numbers is a real number. That is, if I take 2, then if I take 1 by 2, that is the multiplicative inverse. Sorry, here we are telling about the product. So product, so if I take 2 and if I take 3, so 2 into 3, it is 6. So it is also a real number. Then about the multiplicative inverse, every non-zero real number has a real reciprocal. 2 and 1 by 2, you get 1 in the end. So we can say that the real number is a field because it satisfies all the 6 property. Then another example is with integers. So 0 is an integer and sum of two integers will give you integer. Every integer has an integer additive inverse and 1 is an integer. The product of two integers is an integer, but when you take an integer reciprocal, it's not an integer. So if I take 2 and if I have to get a multiplicative inverse, then I should multiply it by 1 by 2. But 1 by 2 is not a integer. So that property is violated. So the set of integers is not a field. Then in the video, this example of then in the video, this example of Z mod 5. Uh, First one is you take any number and then you divide it by 5. Whatever remainder you get, that is this Z mod 5. So the possible reminders that you get in this, so when you add the reminders 0, 1, 2, 3, and 4, when you check the addition property, every value that you get here, so 0 plus 0 is 0, and when you divide it by 5, you get the remainder 0, and then 0 plus 1, you get the remainder 1, 0 plus 2, you get the remainder 2. So every result stay inside that set, because you see here, this is these are the numbers that are already contained in this list of numbers that can form the reminders when divided by 5. So every result stay inside that R5. So it is closed under addition. And if you see 0 is present here, and so you see 1 plus 4, and when you do mod 5, you get 0 here, and 2 plus 3, you get 5. So 5 mod 5, and then 3 plus 2, you get 5, then 5 mod 5, then 4 plus 1, you get 5. So 5 mod 5. So all these cases, there is 0 present. So the additive identity hold. Then 1 plus 4 is equal to 0 mod 5. So 1 and 4 are inverses. And 2 plus 3 So 2 plus 3, you get 0. So 2 and 3 are inverses. So this is the additive inverse, additive identity, and the closure under addition property, and 0 is already there. Now when it comes to multiplication, does every element has a multiplicative inverse, multiplicative identity, all that. So that also hold, every element is present inside this table. Every element that was there in R5 is already here. So that is okay. And then coming to inverse, you take 1 into 1, you get 1. Then 2 into 3, you get 1. And then 4 into 4, you get 1. So for 4 is its own inverse. For 2, 2 and 3 are inverses. So for 1 is its own inverse. So for Z mod 5, all the properties hold. I think this is already in detail. I think in that 45-minute video, this is in detail explained. So you can, I just quickly going through that. So the set of real numbers is a field, and the set of integers is not a field, but the set Z mod 5 is a field. So then is Rn, the integer modulo n, a field for any integer n? So then in the next lecture, uh, the professor in the lecture 3, they discuss about which integers mod n will give a field. So can you tell, uh, for all those people who have already watched the video might be knowing, which integer mod n will give a field? Yeah. So then in the video, they show that only the n where n is a prime number is a field. So you can check this by putting value. So if you are confused, you can put some value for this n. So for example, they show it by taking n is equal to 6. So then take Z mod 6. Then write the table. So the value that can come in the remainder is 0, 1, 2, 3, 4, and 5. So then you do addition. So 0 plus 0, 0, and 0 when you divide it by 5, 6, the remainder is 0. So then 0 plus 1, 1 mod 6 is 1. Similarly, you fill the table, then what we can already say is it is closed under addition because all the elements that are there is already, all the elements that are there in R6 is there in, 1 second. So all the elements that are there in R6 is already there in this addition table. So it is closed under addition, and 0 is present. So the additive identity hold. And then we have also inverses, and we can see that 2 and 4 and 3 and 3. 3 is its own inverse, and 1 and 5 are inverses. But when it comes to the multiplication table, we can see that when you take this row, there is no 1. And for 3 also there is no 1. And for 4 also there is no 1. This means that the row 2, 3 and 4, they don't have a multiplicative inverse. That means none of the value when multiplied and when taken the remainder does not result in 1. So that means there is no multiplicative inverse. So it doesn't satisfy the multiplicative inverse property. So when you put n is equal to 6, it is shown that Z mod 6 is not a field. So then the question is, then what is the difference? Why 5 worked but 6 didn't work? So then there is this greatest common denominator. So that is when you take 2 and 6, it is 2, and 3 and 6, it is 3, and 4 and 6, it is 2. So it is found that RP is a field when P is a prime number. Uh, that is, n should be a prime number for it to satisfy the properties of field. So then the most simple field is R2, which will just consist of two elements, the addition and also the multiplication, and all the 6 properties that comes with it. So the general rule from this lecture is that it is a field when it is a prime number. So if you have doubt, you can then keep on checking by substituting different values of n. So that it's a good practice also to solve the different properties of fields. Okay. So then coming to the concept of vector space. Uh, so then I'll ask, what is a vector space? And maybe one broad question could be, why do you need to learn vector space? Why do you need to know about vector space? We can start with what is a vector space. Okay. So vector space is a set of vector that satisfy two different properties. One is closure under vector addition and closure under scalar multiplication. That is, it is a set of vectors that satisfy these two properties. So if I take two vectors u and v, uh, and they belong to say R2, so then I will have how many components? If I say u and v belong to R2, how many components will be there in U? 2. Yes. So we will have say 2 components. I'm putting some value. So this is my U and V, and this is something that belongs to R2, and I take these two vectors. When I add them, what do I get? I get 4 and 6, which is a vector that again belongs to R2. And then I take some random scalar alpha, which belongs to a field F. This can be anything, a real number or an integer. Sorry, integer is not a field, a real number I take. So I will take some value, say 2, and then 2 times 1 comma 2, that is 2 times u. What do I get? 2 times 2, 2, 2 times 2, 4. So this is again a vector that belongs to R2. So this is a vector space where when you take a set of vectors and you add them, it will be a vector that belongs to the same set, and also when you multiply it by a scalar, it will generate a vector that belong to the same set. So this is what a vector space is. So then one advantage why we why we need to know uh, vector space is that uh, so vector space assumes that these list of vectors satisfy this property or that property, and then all this uh, comes under the assumption of like the linearity assumption. So many things that can be used under the assumptions of linear algebra can be made applicable to these vectors. So if these properties are satisfied in so and so vectors, then whatever that can be accomplished with linear algebra can be used in this also. So you can simplify many things once you assume that it satisfy all these different concepts. So that is why we go into all this. But I think it will become more clear once we deal with uh, some specific concepts one by one. So again, vector space, it has some property commutativity where you take two vectors, u plus v will be equal to v plus u, and then associativity, u plus v plus w will be u plus v plus w. Similarly for multiplication, and then distributive property. So there is also additive identity, additive inverse, multiplicative identity. All these things hold for a vector space as well. So then, what is the difference? So you construct a vector from this field. So here one example is you have the set of real numbers. You pick u1 from R, you pick u2 from R, then you make a product of it, you get u1, u2. That is a two component vector. You make n copies of it, you get an n component vector. So all this is created from the so it's like an object that is created from the set, that is the vector from the field. So then vector addition and scalar multiplication, as I mentioned, if I take this two numbers from R2, it will add component wise and then multiply component wise to each to the scalar. So then the vector space, it should satisfy these property, like it should be closed under addition, and it should be closed under scalar multiplication. It should have an additive identity, a multiplicative identity, and additive inverse, and the other commutativity, associativity, and distributivity. So, if we take the field, it satisfies all the properties of the vector space. And if we take Rn, R2, for example, the plane, the 3D space R3, all these are vector spaces. The origin contains a zero vector. And then any polynomials of degree less than or equal to n, all these are vector spaces. The set of square matrices, it is a vector space. The real symmetric matrices, that is also a vector space. Continuous functions of time f of t, that is also a vector space. The family of lines, that is a vector space. So maybe as an example, I'll give you one question. Okay, maybe let us start from that first patient data. So suppose I have uh, 7 measurements from a patient. It has maybe measurements in the sense the blood glucose level, pressure, etc. So there are 7 such measurements from uh, say 40 patients. Then you created a data matrix. So what is the dimension of the data matrix? Very simple question. So you have 7 measurements. We can call it as M1, M2, M3, etc. up to M7. And you have 40 patients. So you have P1, P2, etc. up to P40. You got a data matrix. You have a data set now. What is the size of this? Yeah, so it is 40 by 7. Okay, you have a vector which is a 2D vector, and it is given by x comma 3. This belongs to 2D. Then is this V. Okay, it's come to uh, is this a vector space? X can be any number from R. Is this a vector space or not? Okay. So the question then might be, does it contain the zero vector? Or else you take any, so V is x comma 3 and x can be any number. So I will take V1 as, say, for example, 2, 3. And V2 is 3, 3. Okay. As per the vector space property, when you add two vectors, you get a vector that belongs to the same set. So when you do V1 plus V2, what will we get? 5, 6. Is it the same as x comma 3? Yeah, this it doesn't matter because this can be 5 because it is mentioned that x can be any real number. This doesn't matter, but this part does matter. It is always 3. So that means that whatever element is there in the set, the second component in that vector is always 3. But the first component can be anything. So that means this set will have what all numbers? I'm summa writing some value. So x1 3, x2 3, x3 3, x4 3. The elements in this set will be like this, where this x1 can be any real number. But when you do the addition, it doesn't satisfy. Or else, uh, if we do the this thing also, if we check the zero vector also, there is no zero vector in this because there is one non-zero element always as the second component. So it's not a vector space. It doesn't satisfy the properties of vector space. So you have this two property. One is this closed under uh, scalar multiplication and another is closed under addition. So if one of the property fails, then you don't have to check all the other property. If one fails, then you can stop there and tell that it's not a vector space. But if one of the property is satisfied, then you must check all the other properties to make sure that it is a vector space. Just like how you uh, prove a theorem. Okay, I'll give another example. You have x, comma, y. Okay, and x is any value that is greater than or equal to 0 and y is any value that is greater than or equal to 0. So this is the set. Is V a vector space? So V contains some 2D vectors. Is it a vector space or not? So you should think of all the properties. You should write down what all are the possible values, what happens when you multiply by a scalar. Okay. So one thing is it should contain the 0 vector. So if we have x and y, if we take x and y, it contains the 0 vector because x can take value greater than or equal to 0, y can take value greater than or equal to 0. So this property is satisfied. And then if I take any value x greater than or equal to 0 and y greater than or equal to 0, I will get a value that is greater than or equal to 0. Because both are positive number, when I add two positive numbers, I will obviously get a positive number. So the closure under addition is also satisfied. That means I have x1, y1, x2, y2, x1 plus x2, y1 plus y2 will be belonging to V because x1 is greater than 0, y1 is x2 is greater than or equal to 0. So obviously this will be a number that is greater than or equal to 0. And this also that. Now, when it comes to scalar multiplication, yeah. So if the scalar is negative, then it will not satisfy the property of that set. That means if I multiply by -1, then I will get, I have x1, y1. This is one vector that I am taking. I am multiplying it by -1, then I will get minus x1 minus y1. Okay. So you get minus x1 minus y1, but does this belong to this set? No, because in this set, the first component must be greater than or equal to 0 and the second component must be greater than or equal to 0. So this scalar multiplication property is not satisfied for this vector space. So it is not a vector space. Yeah. So yeah. So this is not about whether the line passes through the origin, but this is not just a line. So if you consider this x greater than or equal to 0, y greater than or equal to 0, it is this x, y minus x. It is this full quadrant. It's not just a line. So when you have a vector that is like this and you multiply by -1 on any direction, and then when it goes to this space, it is already changed it is already changed that space that it was contained in. So this was the space that it was contained in, but when you did scalar multiplication by a negative number, it changed to this space. So now it is no longer an element of this space. So thus the vector space property is violated there. Even if it is a vector, it is, yeah. So it's not you should not tell it's not a vector. It's not a vector space. It is a vector, but it is not a vector space. Okay. I'm not sure. There is someone named coronavirus waiting to be admitted. So I don't know if I should. I think it would be good if you put the name. Okay, another question. So consider all the vectors that lie on the line y is equal to x. Is it a vector space? Yeah. So this is a example of a vector space which satisfy all the properties. So I hope that is clear. So consider the set of all vectors xy where the total length is 1 or less. That is, if you take a circle with radius 1, should be inside or the boundary of a circle. So the equation is x square plus y square less than or equal to 1. This is the circle with radius 1 and where the inside and the boundary of the circle is within the radius 1. So you should first take vectors that satisfy the equation. That will be the set of vectors x1, y1, x2, y2, etc. So you should first put some values and then find some possible values of x1, y1, x2, y2, etc. And then check the additive property. Yeah. Any question? So you can put some value, for example, 0.80. This is one value that satisfies the equation. And then 0, 0.8. This is also one which satisfies the equation. So this is one vector v1. This is another vector v2. So this is v1, v2. Then does it satisfy the addition, vector addition? Okay, I take v1 itself. So I take two vectors, 0.8, 0. And I add another 0.8, 0.7, 0. What will I get? 1.5, 0. Does this satisfy this? Yeah. So it doesn't satisfy the uh, addition property. So it's not a vector space. So once one of the property is failed, then you can immediately tell that it's not a vector space. But if one property is satisfied, then you should check all the other properties. Okay. Consider set of all. Yeah. You have any doubt? Yeah, you can. I have unmuted. You can ask.
Hello, madam.
Yeah.
You said vector 0.80 satisfies the total length is less than 1. How can it be? That means x square plus y square is equal to 1.
Yeah.
But it is not. No, 0.8 square plus 0 is is less than 1. Okay, okay.
Yeah, it's less than.
It need not be equal to, right. I'm sorry. It is less than 1.
Yeah, it's
X
less than.
square plus y square is less than 1. Okay, okay. Okay. Am I correct, madam? So
Yes,
the
correct.
assumption is 0.8 square plus 0 square
Must
is
be less
less
than
than
1.
or equal to 1.
Yeah.
Okay. Okay, madam. Thank you. Sorry.
Okay. Okay. Okay, then another question is consider the set of all 2D vectors where at least one coordinate is 0. That is x is equal to 0 or y is equal to 0. Is this set a vector space? So you have x, y. This is the set, but x into y must be 0. That means either x should be 0 or y should be 0. Yeah. Okay. So you can take two vectors, for example, 4, comma 0. This satisfy this, right? One of them is 0. Another is maybe 3, 0, 3. This also satisfy this property. And when I add these two, I get 4, comma 3. But here 4 into 3 is not equal to 0. So when you add two vectors that belong to this set, you don't get a vector that belong to this set. So the addition property is fail. Yeah, that is also a reason. But that can be satisfied. So the zero vector property already satisfies because x and y, if both are 0, then it is 0. So here that property is satisfied, but the question is about vector addition. Is that satisfied? Okay. Okay. Next time. So this question is there are a set of 2D points. They sit on the curve y is equal to x square. Is it a vector space? or not. So the set of vectors is x, y, where y is equal to x square. So the vector must be in the form x, x square, like that. Yeah, okay. Yeah. All this is correct. One quick way to check this is I take vector 1, 1, 1, and then I add it, I can multiply it by scalar 2, then I'll get 2, 2. This is not equal to 2, 4, right? Just in the form x, x square. Yeah. So if one of the property fails, then you can show that it's not a vector space. So consider all the 2D vectors x comma y, where x plus y is equal to 5. That is, so you have x comma y, and the condition is x plus y is equal to 5. Yeah, one quick way to check this is 0, 0 does not belong to this set. So it's not a vector space. So consider the set of all 3D vectors x, y, z satisfying the equation x, y, z is equal to 0. Is this a vector space? So if you are telling no, then you should also tell why. So this is the set of all the 3D vectors that satisfy x plus y plus z is equal to 0. So this is a plane, 2D plane passing through the object. So when we consider the 0 vector, when you take 0, 0, 0, this is already uh, satisfied. Like it already satisfies the 0 vector property because 0, 0, 0 belongs to this, like it satisfies this x plus y plus z is equal to 0. So the 0 vector property is fine. Then I will take two vectors, say v1, and I assume it has values x1, y1, z1. Okay. And another set v2, x2, y2, z2. And this one satisfies the x plus y plus z is equal to 0. And this one x2, y2 and z2 also satisfy the property x plus y plus z is equal to 0. Now, when v1 plus v2 I take, I will get x1 plus x2, y1 plus y2, z1 plus z2, right? And the property is that, so x1 plus x2, y1 plus y2, z1 plus z2. And uh, so this should satisfy this, right? So when I expand and when I write it, x1 plus x2 plus y1 plus y2 plus z1 plus z2 must be equal to 0. But I already know this satisfies this one, this satisfies this one. So x1 plus x1 plus y1 plus z1, this three terms, and x2 plus y2 plus z2, this three terms. This already satisfies 0. So then this will also satisfy this property. So vector addition also hold. It will result in a vector, a resultant vector that satisfy x plus y plus z is equal to 0. Okay. Yeah. One example, v1 is 1 minus 1 0, v2 is 2 minus 2 0. But in this case, since it satisfies the vector addition property, taking examples like this with some numerical value will work. But then in some cases, it is better to use general notation like x1, x2, y1, y2, etc. Then you might see that in some cases, for like luckily some values might work and you get result, but it may not work in all the cases. So it's better to put x1, x2 like a general notation rather than putting 1 minus 1, etc. Then coming to the scalar multiplication case, you have, you can take v1 as x1, y1, z1. Then you multiply by some general c, a scalar c, which belongs to any real number. So c times v1 will give what? C times x1, c times y1, c times z1. Now, when I add this cx1 plus cy1 plus cz1, c is common, so I can take c outside, x1 plus y1 plus z1. This I know is 0, so c is 0, I get 0. So again, scalar multiplication is also satisfied. So this set of all the 3D vectors x, y, z that satisfy the equation x plus y plus z is equal to 0 is a vector space. Okay, I'll give one more example. So the set of all 3D vectors x, y, z satisfying x plus y plus z is equal to 1. Is this a vector space? Yeah, there is no zero vector that satisfy x plus y plus z is equal to 1. So you can immediately tell that it's not a vector space. So the question is about if I do a set of operations like uh, addition and scalar multiplication, if I manipulate the vectors in this set, is the resultant vector inside the same set? That is the question that we are trying to test here by checking whether something, a set, is a vector space or not. So I'll just write it down. So the main point is this: if I combine or if I scale my data inside this set, am I guaranteed to stay inside the set? Or will these operations or manipulations break the system? So this is what we are checking. If I do certain operations on the data set, will it break the data set or will it work without any issue? So if I do the operation and then uh, things are okay, then I can make use of many uh, properties and many operations that can be done within this space. Uh, so this space, in the sense, we define a space to have certain property. You can do certain operations in this space. And finally, you get a data set and you see if your data set satisfy all this property, then whatever you apply to this space can be applied to your data set also. So this is what we this is why we learn what vector space is. So it's like you apply some linear transformations to your data only if it satisfy certain properties of linearity, right? So that is what this is checking. When you define a data, when you want to do some transformations on the data, you need the data set to satisfy certain properties of that space. And that is what we are checking. Um, and these are some things that need to be satisfied when we do some techniques, like, for example, when we take dimensionality uh, reduction. So in that case, in case of dimensionality reduction, you have a very large data set, but you want to reduce the data set to a lower dimensional where you can better explain the data. But for this to be done, the data should satisfy certain property. So, and vector spaces, so if you can show that your data fit inside the properties of a vector space, I'm just telling this as an example. This is not that simple. But if the data satisfy these properties of vector spaces, then whatever transformation or whatever linear operations that you can do under the vector space applies to your data set also. So this is the reason we study all this, because valid vector spaces, they contain small subspaces. We can make use of many principles such as principal component analysis, etc., that can, like, lower your dimension from, or lower, or make compress your data from a very high dimension to a very lower dimension. Uh, I don't know what I mean by higher dimension, lower dimension is you have so in the initially you I mean initially we had this concept of a data matrix where we had different features f1, f2. This is what we have mentioned earlier as the heart rate, the oxygen level, the glucose level, all those. So I'm calling it as features f1, f2, f3, etc. up to say F100. I'm measuring 100 different values from patients, and I have 100 patients. So maybe I'll take 1000 patients. So right now I have a data set which is of size 1000 by 100. Now this 100 might also have, it's not necessary that all the 100 measurements that I took from the patient are like very distinct, or they contain unique information. So some feature might contain information that is related to another feature. So F1 might be some value that is 2 times F2. That means I'm having some duplicate information. I don't need both F1 and F2. I need only F1. I don't need F2. F2 I can derive from F1. So this means you reduce your dimension, that is this 100, you can reduce it to 99 by removing F2 because you can get F2 from F1. So that is what I meant by lowering the dimension. That is, you remove some redundant or duplicate information and then you move from a higher dimension to lower dimension. So this is one example um, where this is done through one way with principal component analysis. And for principal component analysis to be applied, your data must satisfy some properties of the vector space. So that is why we start with the concept of vector space, because if we can show that our data is something uh, that is contained inside the properties of linearity or a linear vector space, then we can use many things, many transformations that are applicable for that space. So, yeah, so this is why the concept of vector space is there. Now, um, there is this, uh, there are other things. So, for example, there is subspace. We'll come to this in the next class. So you have this vector space of numbers, but sometimes you want to constrain yourself to a subspace, a small space. For example, uh, your data might contain only odd numbers. So you don't want to take the full data set of, I mean, not the full data set. You don't need to consider the full realm of integers. You can restrict your space to the set of odd numbers because your data contains only that. Then you can play with properties that are applicable for that small space. That is a subspace. So subspace itself is a vector space, but it is just a subset of a vector space. It is also a vector space, but it is a small space compared to a large vector space because you want to uh, restrict yourself to a small space because your data is only contained within that small subspace. So that is the subspace. We will discuss in detail. I mean, we will do some example questions like today for vector, like we did for vector space. So we'll discuss about subspace and then uh, followed by linear combination and basis. Linear dependency and basis we'll do in the next class. So I will upload the video and also the contents of the slide, and I will try to add some more practice questions for vector space, so that you understand the vector space concept more clearly in the next class. So we can continue discussing about subspace. Yeah, so thank you for attending today's session. Next session will be on next Tuesday, same time, 7 p.m. to 9 p.m. Thank you.